All right, let's see if we can pick up where we left off. The Bohr model of the atom in 1913 indicated that each electron had to be a specific distance from the nucleus. These were called energy levels. This is the model that we commonly use whenever we're putting an atom on a two-dimensional surface like a whiteboard or the desktop or something like that. We use the Bohr model because it just gives us it shows us that atoms or electrons can only be in certain places around the nucleus, that we have specific energy levels, and that a certain number of electrons can only be in each energy level. This first energy level, for instance, can only hold 2 electrons, and then the next energy level holds a total of 8 electrons. Then come along in 1926, and we have Schrödinger. Schrödinger created the quantum model of the atom, which kind of continues to build. So the more we learn about the model of the atom, the more we have to change our model. The quantum model presents the atom with the nucleus, and then surrounding the nucleus we have electrons that are in this electron cloud, and they have a specific shape. Each part of the electron cloud, each energy level, which Bohr knew existed, has a specific shape, which some of them are spherical, some of them are shaped like teardrops, some are shaped like donuts, some are shaped like dumbbells and things. So they have different shapes, and the electron can literally be anywhere within that shape, a certain distance from the nucleus. And so it's the place where electrons are is more like a probability than a specific spot. And that's the quantum model. Typically, when we're teaching about atoms and whatnot like that, when you're teaching students, particularly younger students, it's the Bohr model that we're going to use because it does show us how electrons fit in energy levels around the nucleus. So all of that to show you how our view of an atom has changed through the centuries. So when we look at the information that's in the periodic table, we have the atomic number. The atomic number tells us the number of protons, so that's an important piece. I mentioned that earlier. This distinguishes every element from the other. Every element has its own atomic number. Atomic number is how the periodic table is put together. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so 9, 10, so on and so forth. You have each of the elements having its own particular atomic number, and that's because each element has its own number of protons. No two elements can have the same number of protons. The atomic number, as long as an atom is electrically neutral, the atomic number will also tell me the number of electrons that it has, because you have the same number of electrons as you do protons as long as the atom is neutral. That atomic mass, which is the other number that you see, the larger of the numbers that you see in the periodic table with each one of the squares. The atomic mass essentially tells me the total number of things that are inside the nucleus, but it's an average when we take a look at all the naturally occurring isotopes for that particular atom. That's why we have you have fractions. So for instance, if we take a look at hydrogen, typical symbol for hydrogen on the periodic table, we have the square, and you will have the elemental symbol, which for hydrogen is simply H. We have the atomic number 1, which tells me that I have 1 proton in an atom of hydrogen, and as long as it's neutral, that tells me that I'm only going to have 1 electron. The atomic mass down here is 1.008. That tells me that the average mass of the nucleus of this atom is going to be 1.008, which means that in a typical atom of hydrogen, I've got one thing in the nucleus, and since I know it's got to be a proton, it also tells me that I don't have any neutrons in this. So the way that I can determine neutrons, at least for the most abundant isotope, is take your atomic mass, take that atomic mass, round it to the nearest whole number, 1.008 rounds to 1, subtract the atomic number 1 minus 1, in this case it would be 0, and that tells me that I have 0 neutrons in a normal atom of hydrogen. So in a typical atom of hydrogen, I don't have any neutrons. So 1 minus 1 is equal to 0. So what then are isotopes? Isotopes are atoms of the same element, which means they have the same number of protons, but they have different numbers of neutrons. So isotopes have different numbers of neutrons. That's the line you need to remember. Isotopes have different numbers of neutrons. Same number of protons, different number of neutrons. So if we take a look at this example that I put here, there are 3 different kinds of hydrogen. Normal hydrogen, or hydrogen 1, has 1 proton and no neutrons. So this particular way to write an element symbol is called isotopic notation, in which case the mass number goes on top and the atomic number goes on the bottom. So this is not the same way that we see it on the periodic table, and that's what we have here. So the atomic mass, or the mass number rather, would be on top, and the atomic number, which is the number of protons, would be here on the bottom. Hydrogen 2, which is a different isotope of hydrogen, has 1 proton and 1 neutron. Well, we have the mass number of 2, and we still have only 1 proton. So notice that the bottom number across all of these hydrogens is 1. That's because that's the atomic number. If it has an atomic number of anything other than 1, it's not hydrogen. But 2 minus 1 is 1. So that tells me that this has 1 neutron, and there you see that right there. Hydrogen 3 has an atomic mass of 3 and an atomic number still 1 because it's hydrogen. Well, 3 minus 1 is 2. So, and if we take a look just above that, this hydrogen has 1 proton and 2 neutrons, and that has a mass number of 3. So that is my isotope of hydrogen 3, which we refer to as tritium. This tritium, this is the type of hydrogen that was used in hydrogen bombs because it's highly radioactive. So these are called isotopes, and we give each isotope a name by calling the element name and then a dash and then its mass number. So hydrogen 1 has a mass number of 1. Hydrogen 2 has a mass number, or that mass of 2. Hydrogen 3 has a mass number of 3. Okay? But all of them have atomic number 1. They all have atomic number 1 because of the fact that it is hydrogen. So what do we need to make sure that we learn from this particular slide? First, isotopes are atoms of the same element, therefore the same atomic number, that have different numbers of neutrons. Isotopes have different numbers of neutrons. So atoms of the same element with different numbers of neutrons. Those are isotopes. All right, let's go back to our mixture. So what do we have when we have something that's called a mixture? Mixtures have various substances in them that can be separated by physical means. So a homogeneous mixture is the same throughout. A good way to think about that is solution. Salt, water, tea, coffee. This is a solution. It's the same throughout. Okay, it's the same throughout. I can't filter it. If I poured this coffee through a filter, I'm not going to get the coffee out of it. What I'm going to get coming through the filter is still going to be coffee. But if I take this coffee and I boil off the water, what I'm going to end up with are all of the solutes that made it coffee at the bottom. Whereas a heterogeneous or heterogeneous mixture is a mixture that I can separate by physical means that you can actually see. It's not the same throughout. So mixtures can all be separated by physical means. Things like soil, I can physically pick out the big rocks and the smaller rocks, etc. Chicken soup, I can physically pick out the pieces of chicken and the carrots and the tomatoes and whatever else is in the chicken soup. So if it's not the same throughout, then it would be considered a heterogeneous or heterogeneous mixture. And if it's the same throughout, it is a homogeneous mixture. Solutions versus suspensions. A solution is a homogeneous mixture. For instance, if I put Kool-Aid into water, then what I have is a solution. Now, the two parts of any solution, the solute, which is the part that gets dissolved, and the solvent, which is the thing that does the dissolving. A better way to think about that is typically when you're making a solution, whatever you have the most of, we consider that the solvent, and whatever you have the least of, we consider that the solute. But if I put sugar into water and stir it around, the sugar will dissolve, and so the sugar is the solute, and then the solvent is the water. If I have a suspension, then what I've got is something that won't dissolve. Think about Italian salad dressing. Italian salad dressing is a suspension because the particles of oil and whatnot like that are not going to dissolve in the water because oil doesn't dissolve in water, and so you end up with these particles that are suspended throughout the mixture, and so what you have is called a suspension. Physical, chemical, and nuclear changes. One of the things that you will have to teach, regardless of the level, most likely when you're dealing with physical sciences, is the difference between physical changes and chemical changes. A physical change does not result in the change of any type of matter. Like, for instance, if I take a piece of paper and I cut a piece of paper apart into smaller pieces of paper, it's still paper. If I take wood and I chop that wood up, I've still just got wood. If I take water and I freeze it into solid water or ice, it's still dihydrogen monoxide. It's still H2O. I have not changed the chemical makeup of it. Okay? If I take that ice and I melt it into water, it's still H2O. It's nothing different. So that is a physical change. Physical changes are changes that do not change the chemical composition of whatever you're working with. Now, don't fall into the misinterpretation of this saying that physical changes can be undone. Okay, no, let's not do that. Because if I were to take a piece of paper and I cut it into smaller pieces, there's nothing that you're going to be able to do right there that's going to be able to undo that cutting. But it's still a physical change. I've got still it's paper. Now I could undo it, but it's going to take some doing. You can't readily fix that. You would have to take it apart, take the paper apart and reform it into paper and whatnot like that. So that's a physical change. Chemical changes literally changes the chemistry, the chemical makeup of whatever it is that you've got. If I take those pieces of paper and I burn it, I set fire to it, now I've got a chemical reaction happening, combustion. And what I end up with at the end isn't the same paper anymore. It's what you get at the end of this chemical reaction. Okay, so that is not paper anymore. Now I have a bunch of carbon because I've taken the carbon that was in the cellulose has now converted into CO2 plus charcoal plus it has released some carbon into the atmosphere. So I've chemically changed it. It has different properties. Chemical changes, things like burning things, cooking something. When food spoils, when you stick food in the refrigerator and you forget that it was there, and after a while you come back and you look at that pork chop that you were going to eat, maybe, and it's green and fuzzy. I wouldn't eat it. But that's something has grown on it. Yeah, so you have actually chemically changed that pork chop. Or maybe you didn't chemically change it, but it has chemically changed. So that is a chemical reaction. That's a chemical change. Chemical changes can be either reversed or whatever, but only by chemical means. It would be very difficult to undo some chemical changes. If I take something and I take a piece of wood and I set it on fire and it combusts, you're not going to be able to just get that back in any way. There's the chemical reactions that would be necessary for that are a little rough, so you're not going to be able to do that. And that's why, but there are some chemical reactions, like if I make a chemical compound from two other compounds, there are chemical reactions that I can reverse. they're still chemical reactions. So don't fall into the idea of if I can undo it, it's physical, and if I can't undo it, it's chemical, because that's an oversimplification. If I can undo it with physical means, or rather, more importantly, if I don't change it chemically, it's a physical change. If it is changed chemically, then it's a chemical change. Then there's nuclear changes. These are something that happens to the nucleus of an atom. When the nucleus of an atom splits apart, that's called fission. This takes place in nuclear power plants. This is how we get energy. This takes place in nuclear bombs. Because when a nucleus splits, the mass that you have left is different from the mass that we started with, and that difference in mass is released as energy in that famous equation, E is equal to mc squared. Thank you, Albert Einstein. And so it releases a massive amount of energy, which is why nuclear changes are very energetic. Then you have fusion reactions, which happen when you take two nuclei and you fuse them into one nucleus. This is what's happening in stars. And then they also release energy because the resulting nucleus has less mass than what we started with the two separate nuclei. So as a result, that excess mass is converted directly into energy. Again, equals mc squared. Energy is equal to mass times the speed of light squared. And that's how much energy is released. So nuclear changes occur when you have either fission, where one nucleus comes apart, or fusion, where two nuclei are fused into one nucleus. Okay, two nuclei are fused into one nucleus. So we have physical changes, chemical changes, and nuclear changes. You're probably not going to run across too many nuclear changes. All right, so for chemical changes and all chemical reactions, we will be relying on valence electrons. Valence electrons are the electrons that are involved in chemical reactions. Chemicals, each element is chemically reactive based on the number of valence electrons that it has. So what are valence electrons? Valence electrons are the outermost electrons in an atom. Those that are the farthest away from the nucleus are referred to as the valence electrons. Those that are in the outermost electron shell. For every atom, there's something called the octet rule. That is that an atom is most stable when it has a full outer shell of electrons. Even if it makes it become electrically positive or electrically negative by adding or taking away electrons. Adding electrons makes it electrically negative. Taking away electrons makes it electrically positive. But an atom is most stable when it has a full electron shell. And that full outer electron shell is going to be holding 8 electrons. So hence the octet rule. So atoms are most stable when they have 8 electrons in their outermost shell. They could either gain or lose electrons in order to get there. For an instance, sodium. Sodium loses 1 electron in order to have a full outer shell. And when it loses 1 electron to do that, it ends up with a positive 1 charge. That means that sodium in its most stable state is sodium plus 1. So if we take a look, sodium's outermost shell has 1 electron in it. And then so it's easy to lose that electron. And so we end up then with 8 electrons in its outermost shell. And that gives us sodium plus 1 because it lost 1 of its electrons. And so that becomes the most stable form of sodium. Metals, nonmetals, and metalloids. I showed you this when we first looked at the periodic table. The left-hand side of your periodic table are all metals. The left-hand side of your periodic table are metals. Most elements on the periodic table are metal. Most elements on the periodic table are metal. They go clear across the periodic table from the left-hand side all the way through the middle into the right-hand side to a diagonal mark. And those would be all of your metals. Non-metals would be on the extreme right-hand side of the periodic table. Metalloids are right down the zigzag line, the metalloid line. Noble gases are the gases that are on the extreme far right of the periodic table, starting with neon and going down to oganesson. So those are the noble gases. They're so called because they don't react with anything. They have a full outer shell. Their outer shell has 8 electrons in them normally, and so they don't react with anything. When we're talking about the left-hand side of the periodic table, it's easy to lose electrons and become positive, which is what happens with all of the metals. Metals will lose electrons and become positive ions, and that makes them more stable. Non-metals, those things on the right-hand side of the periodic table, other than the noble gases, will tend to gain electrons, and they become negative. Okay, things like oxygen. Oxygen tends to gain 2 electrons and become oxygen minus 2. Fluorine gains an electron and becomes fluorine minus 1. So everything that's in that, everything except that far right hand side, which are noble gases. So starting with fluorine, chlorine, everything down that line, which are referred to as halogens, they tend to gain 1 electron, and that makes them more stable. So they're non-metals and they gain electrons. Metals, everything on the right-hand side of the periodic, the left-hand side of the periodic table, they will lose electrons. Metals tend not to hold on to their electrons very tightly and become positive. So, and this is what I just said. Families 1, 2, and 3 tend to lose electrons and become positive. Families 5, 6, and 7 tend to gain electrons and form negative ions, and those are nonmetals. The metalloids are that line that's in between. It's kind of a zigzag line. It's not a straight column, and they form the metalloids, and they have some characteristics of metals and some characteristics of nonmetals. So if we look here at this periodic table, your metalloids, you form a line that's right here, starting topping off aluminum, coming down, coming across. So silicon and germanium are both metalloids. Arsenic and antimony are metalloids. Polonium, tellurium, metalloids. And astatine is often considered a metalloid. I'm not going to go down any further because tennessine is both man-made and it's very unstable, so you hardly ever see that anywhere. But these are your metalloids. So silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. So those are your metalloids. Your metals would be everything to the left of that line, including this first column, which are the first column, which are your alkali metals, the second column, which are alkaline earth metals, everything in the middle here, which are referred to as transition metals. All of these are metals. And then over here on the far right, here are our noble gases: helium, neon, argon, krypton, xenon, radon, oganesson. And then the halogens: fluorine, chlorine, bromine, iodine. These are your halogens. And then what you see over here, these are our non-metals. Okay. Carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, bromine, iodine. Okay, so these are your non-metals. So chemical bonding. How do chemicals bond together? In order to make compounds, chemical elements have to actually bond together. This is always going to take place with our valence electrons. So we have 3 types of bonds, only 2 of which will you typically ever come into contact with: ionic bonds and covalent bonds. Ionic bonds are essentially like static electricity. You're not sharing electrons here. You have a metal from the left-hand side of the periodic table that loses electrons and becomes positive. You have a non-metal from the right-hand side of the periodic table that gains an electron and becomes negative. And the negative and positive charges pull it together. So you end up with these two things that are pulled together by positive and negative charges. That's an ionic compound, okay? It's an electrostatic force. It's very strong, but you can, as that, depending on, and they're always happen in the same ratio, and that ratio depends on how positive and how negative the two that are involved are. Covalent bonding, this is bonding that happens when valence electrons are shared between two atoms. Okay, when electrons are shared between two atoms, so that both atoms that are involved in the sharing end up with an octet of electrons around them. One atom doesn't give up electrons, one atom doesn't gain electrons. They actually share those electrons, and so the electrons, if you're looking out from one of the atoms, it has a full octet. If you look out from the other atom, it has a full octet because they're sharing electrons. That's called covalent bonding. Now, the metallic bonds, this is a completely different kind of bond. And what this means, what this truly is that when you have a metal, electrons can be easily bounced from one atom to another with a metal. Metal to metal bonds are when the electrons can quickly and easily move from one to another. This is why metals are so great when it comes to conducting electricity, because what electricity is simply moving electrons. So when electrons move from one atom to another down a wire, well, what do you have? Electricity. So usually metallic bonds are going to be found obviously between metals, and usually it's the same type of atom. So this is the way that metal atoms stick together to make that particular metal. But it also makes metals makes them highly able to conduct electrical currents, makes them highly conductive. So here's an example of ionic bonding, and this is why we don't call this. This is why we don't call this a